program Brian wrote was for a Ferranti Sirius computer in 1961. His primary interests have always been compilers and operating systems, and he's written several of each. The compiler for GENTRAN, the programming language at the heart of GENESYS, was his first. Now he's moving on to part 2 of his talk. So I'd like to say, if any of you have any questions, if you're participating by Zoom, please put them in chat as we go along, and they'll be dealt with at the end. And if you're here, please ask your questions at the end. So I'll hand over to Brian.
Thank you very much, and welcome everybody. Last November, we left the story of GENESYS at the time when the contract had been let and the implementation team was in place. And work was about to start. The GENESYS Centre in Loughborough was in the planning stage, getting ready to take the system over when we had built it. But before I start, I would like to say a few words about my lifelong friend, Peter Grigono, who died at his home in Montreal earlier this year of cancer. I met Peter in 1962 at Queen's College in Cambridge. I'd been there for a year when Peter arrived, also to study mathematics. We discovered a shared interest in the theatre, and neither of us could act for toffee, but we found that we worked together well, and for our 2 shared years, we were much in demand backstage. Peter would be sound, I would be lights, Peter would be lights, I would be stage manage, and so on. After college, we kept in touch, and Peter even took over my bedsit in Notting Hill when I moved out. He joined the GENESYS team towards the end of the project, and only part-time. His other part-time job was with Peter Zinoviev, the renowned British composer and pioneer of electronic music, who also died earlier this year, just a few months after Peter Grigono. Peter Zinoviev founded the Electronic Music Studio, which is actually the basement of his house in Putney. He developed synthesizers such as the VCS-3 used by David Bowie and other popular entertainers. Peter Grigono recalled meetings with several, including Ringo Starr. The Science Museum has a cabinet dedicated to EMS and its products. As well as helping in the development of synthesizers, Peter Grigono was programming the 2 DEC computers you can see in the picture, a PDP-8S and a PDP-8L. He developed a program for scoring electronic music and playing the scored music back through synthesizers connected to the computer. He named the software MUSIS and published a paper about it in Software Practice and Experience. Because he was working simultaneously on software called GENESYS, MUSIS was, he used to say with a chuckle, the only possible name. The notation that Peter devised was simple enough for composers with no programming or indeed computing experience to learn in a few hours. MUSIS was the basis of many original electronic performances, including Medusa by Harrison Birtwistle, performed in June 1970 at the Queen Elizabeth Hall in London, and Tesserae 4 by Justin Connolly, performed in March 1972 in New York. While keeping 2 jobs going, Peter met and fell in love with the Canadian poet Sharon Nelson. They married in 1972 and decided to settle in Montreal. The best-known university in Montreal is McGill, but there are 2 others, and one is named Concordia. It was formed by merging 2 established colleges with different backgrounds, one French and Catholic, the other English and Protestant. Peter joined Concordia as a lecturer, and by 2004 he was Professor of Computer Science. His first book was Programming in Pascal, published in 1978 by Addison Wesley. It was translated into 8 languages, finally selling around 500,000 copies. And in 1980, Hewlett-Packard adopted the book as the manual for their Pascal 1000 compiler. Peter devised several programming languages. MUSIS evolved into a general-purpose language for microcomputers called Mouse. and his first object-oriented language was D, named after Queen Elizabeth I's chief scientific advisor, John D. He was a wonderful teacher, much loved by his students. And in 1997, the Faculty of Engineering and Computer Science introduced a Teaching Excellence Award, and Peter was its first winner. In 2006, the university introduced a President's Teaching Award, and Peter was the first to receive that too. On a trip to Montreal in 2005, I gave a lecture at Concordia entitled Towards Malleable Software, a title I was planning to use in a book. Don't write the book, said Peter, write the software. Forgive me, my clicker has decided to stop working. And so began a project that lasted until his death. It has provided several PhD students with material for their theses and many papers. We named the project the Erasmus Project in recognition of our first meeting at Queen's College, where the Dutch humanist, philosopher and man of letters, Desiderius Erasmus, lived for several years. The programming language within the project should logically have been called Desiderius, but as no one would be able to spell that, we settled on Desi. Peter was a superb software engineer, a wonderful teacher, and is hugely missed by all who knew him. Work started on implementing GENESYS on the 10th of July 1969, and most GENESYS development took place in the area of London between Victoria Station and St James's Park. This modern walk, recommended by Ramble London, traverses key locations with uncanny precision. The walk starts a few yards from the Offices of Computation Research and Development in Dartmouth Street, where we had developed the GENESYS prototype SPAN on their CDC 3300 computer. Along Petty France and then back along Caxton Street past the Alcock, Shearing and Partners office, which was our third. The walk winds through the Peabody estate, which has been providing affordable housing for London's poor for more than 150 years. In 1969, it had an excellent street market. Then past the Army and Navy store with its food stall and wine cellar. Walking around Westminster Cathedral brings us to Ashley Place, where we had our second office, before it was knocked down to make way for a McDonald's. Then along Morpeth Terrace to Morpeth Mansions, where Betty and I had the corner flat on the first floor. It was not quite living over the shop, but something that sometimes rather felt like that. And the walk finishes close to the offices of the Computing Service SIA in Ebury Gate. We had used their CDC 6600 to develop the second GENESYS prototype called Cleat, and this was to be the principal development machine for GENESYS itself. We called it the mother machine to distinguish it from the other computers we were contracted to get GENESYS to work on. The programmer of today uses powerful integrated development environments on a multi-monitor computer, but programming was rather different in 1969. The design of GENESYS was done in a collegiate way around a whiteboard. Typically, 3 or 4 of us would get together to work on some feature. We had a rule that every idea must be written on the whiteboard. And when the board became full, we took a snapshot using a Polaroid instant camera, and I used the snapshot to write minutes of the meeting. Our secretarial team typed my notes using an IBM golf ball typewriter, photocopied them, and distributed copies to the team. The original typescript was added to the minutes and decisions archive known as the MAD file. Every design document, flowchart, or line of code was written in pencil, So everyone had a pencil and eraser, and each office had a pencil sharpener. Design documents and flowcharts were written on pre-printed pads. And rather than being lined sheets, which would interfere with the layout of flowcharts and structure of diagrams, every sheet of the pre-printed pads had a matrix of processed blue lines printed on its reverse. This was just visible when writing on the front of the sheet and provided a guide for lines of text and for flowcharts. Some programmers preferred to use a template, but most just relied on the blue matrix. Lines of code were written on pre-printed coding sheets in pencil. And although the punching of programs into cards was usually delegated to professional punch operators at the computer bureau, we had a hand punch for producing a few cards associated with changes during debugging. Another vital item of technology was the telephone. There were no mobile telephones in those days, and if the office needed to get in touch, then they would phone the operator at SIA, who would announce over the public address system, "Telephone call for Mr. Shearing." Sometimes anyone on the team would do, and a protocol to achieve that was needed. And the arrival on television in 1969 of Monty Python's Flying Circus came to the rescue. As I'm sure you will all remember, one regular character was Spiny Norman, a giant, rather depressed hedgehog. Norman was adopted by the GENESYS team, and the secretarial team briefed accordingly. And to get hold of any one of us, the corridors and offices of SIA would resound to the announcement, "Telephone call for Mr. Norman Spiny." Now, GENESYS was a software framework in which programmers could write programs for engineering applications. And this is just a little reminder of what we had last November. Programs written for GENESYS were called subsystems, and by 1978, 25 were available in 6 categories. And GENESYS was not only a framework for programmers, but also a framework in which engineers could use its subsystems. Before GENESYS, most engineering programs worked on only one or perhaps 2 kinds of computer. Most programs were written in Fortran, and each computer manufacturer provided a compiler for Fortran, which seldom matched the detail of other manufacturers, in spite of the efforts of standardization committees. But a program written for GENESYS would run unmodified on 6 different kinds of computer under 10 different operating systems, and later it was ported to several more. The minimum configuration comprised a processor together with 4 magnetic tape decks or 1 disk. Input was from paper tape or cards, and later by interactive terminal. Output was to a line printer and to paper tape or cards. 1 tape deck, or file on disk, held the GENESYS software and 1 or more subsystems. 1 deck held a scratch tape used to hold overflow from the often far too small main store. This was virtual storage based not on paging, but on variable length records corresponding to vectors or columns of a table. At the end of a run, the user could choose to save the complete state of computation so that a subsequent run could resume with that as the starting point. We adopted the technology of the time in which there were neither mothers and daughters, nor parents and children. Worse yet, there were grandfathers too. The convention of the day was to reuse the grandfather tape as a new son, and thus a cycle of 3 tapes could be used indefinitely, with grandfather always off the machine as backup. An engineer using a GENESYS subsystem presented data in the form of tables and commands, and each table had a name embedded in apostrophes, and a command carried out an operation on a nominated table. And here is a complete GENESYS run that uses the hypothetical system called Abacus. Data are organized into areas. The start area is administrative. In this case, the user is giving the job a title, which will appear at the head of every page of output. And the tables area has tables of data, and the master area has commands to be applied to the data. Instead of writing *exit to leave the subsystem, the user could nominate a son file in the start line and write *save instead. This would cause the state of the system, including all of its tables, to be preserved on the nominated file. On a subsequent run, execution could be resumed by nominating the saved file as father. The start area could include editing statements that applied to tables, macros, or GENTRAN programs. And here is a complete GENESYS job that creates B file as a copy of A file, but without table ABC. We saw last November that the engineer could replace an item of data with a name and experiment with the item taking various values. Most commands were procedures, but it was also possible to define a command that returned a value. This example illustrates the Fortran-like features of the GENESYS command language. To avoid repeating groups of commands, GENESYS allowed the engineer to name a group as a macro. In this example, the macro solve is short for 4 commands. Any item of data could be written as an expression in terms of values, variables, and mathematical functions. The manual for a subsystem would declare units for values that had dimensionality. Dimensionality was a combination of length, force, time, temperature difference, and angle. And the engineer could decide to use the default or choose any other dimension with the same dimensionality. To create a subsystem, a GENESYS programmer defined its tables and its commands and provided code to effect each command. Tables and commands were defined in the definitions area. And code was written in the overlay area. The programming language was GENTRAN, a portable dialect of Fortran. GENESYS was delivered as a single program containing the system itself and one or more subsystems. The program consisted of code that was always in memory and a number of overlays of which only one was in memory at any time. The first 9 overlays, together with the resident code, comprised GENESYS itself. There was an overlay to process each area. A subsystem comprised an overlay containing the definitions of its tables and commands and one or more overlays of code. And overlay 10 was an index that related the name of each overlay to its position in the file. We spent the first 6 weeks of the project building an overall design and implementation plan. And here is my manuscript of the minutes of a meeting on day 1, by which I mean the first day on which we were being paid. The first issue discussed showed how concerned we were about getting GENESYS to work across all the computers we were contracted to support. Rather than getting the system to work on the mother computer at SIA and then porting it to the other computers, Terry was keen that we should launch pilot projects on all of the computers straight away. We settled on a strict regime of top-down development. Improvements were relegated to the end of the list and only considered as maybes. We were determined from the start that striving for perfection should not get in the way of timely delivery. In the afternoon of day 1, we drew up a list of deliverables, starting with 63 documents. We dubbed the subsystem for frame analysis the workhorse. We had included this in our quotation for the GENESYS contract. We wanted to ensure that all of our programmers spent time using the tools they were developing. And for a while, we had a policy of 1 week on the workhorse for every 3 weeks spent working on the system. And we also identified some 25 items of software. On the morning of day 2, we started figuring out relationships between the major components of the system. And in the afternoon, we considered how we would deal with errors, which could arise from mistakes by an engineer, mistakes by a subsystem programmer, or mistakes by us. This was before programming languages included constructs for exception handling. In those days, handling errors had to be considered early in the software design at the architectural level. Day 5 saw more of the team in attendance at the planning and design meeting. We refined our list of deliverables. We declared who was responsible for each one and mapped their dependencies. On day 7, we estimated the time needed for each item of work and produced a plan that ran from September 1969 until December 1970. We did not meet that initial deadline, but by early in 1971, we were able to make a version of the system available to the GENESYS Centre on the CDC computer at SIA. And later that year, we were able to provide a version on the ICL 1900 range. And this meant that the GENESYS Centre could use GENESYS on the Loughborough University computer. But progress in those first few weeks had not been without interruption. On the 16th of July 1969, the first man walked on the moon. My minutes for the following day report that not a lot of work was done that day. I mentioned this to Barry, and he said that he remembered the day well, because Don and I had taken the whole team out to lunch. I smiled at that recollection of the event, which I had forgotten. And then Barry added that he remembered the occasion particularly well because it was the only one on which Don and I had done so. Oh dear. So far, there have been 11 major dialects of Fortran. The first 4 were IBM's, and subsequent dialects have been determined by a standards committee, which has representation from IBM, but also from other suppliers. The dialect supported by the computers we built GENESYS on was Fortran 66, the first dialect with community involvement. The remaining Fortran standards have been promulgated by ASA's successor, ANSI. While we were developing GENESYS, the ASA decided to rebrand as ANS. The American Nuclear Society took umbrage at this, claiming prior usage, and their claim was upheld. Another rebranding was called for, resulting in the USASI, which eventually became ANSI. It was interesting how much trouble the primary standards organization in the United States seemed to have had in standardizing their own name. The problem with Fortran 66 was not the standard itself, but with the weak compliance by manufacturers claiming to be consistent with it. The BCS Fortran Specialist Group had its first meeting on the 6th of January 1970, where it was decided to produce a report to review existing implementations of Fortran against the standard. A committee was set up with me as chairman and David Muxworthy of the Edinburgh Regional Computing Centre as secretary. Meetings were held in our offices in Caxton Street. And these were the 6 compilers that the report compared against the standard. You'll not be surprised to see that the list is precisely the 6 compilers we were building GENESYS for. We did include another chapter about 8 other compilers that we had less detailed knowledge of. Several years ago, David and I lodged correspondence and papers from our time together writing this report with the National Museum of Computing at Bletchley Park. And in the schedule of my documents sent to the museum, I noticed that the 1966 standard came from ANSY's short-lived time masquerading as the American Nuclear Society. The GENESYS team needed to know whether there was a subset of Fortran that worked on all 6 machines. It turned out there was indeed a portable intersection of dialects, but it was small and included neither input, output, nor string handling. It was little surprise that consistency in handling characters was almost unachievable. Portability only came with the adoption of 8-bit characters and 32-bit words. But GENESYS could not wait for this convergence of hardware design. So here is a recipe for building a portable system without the help of a portable programming language. First, define the portable intersection of the Fortran dialects of each targeted computer, and name the intersection the dialect for system programming, DSP. Define a new language, named GENTRAN, to be the dialect for system programming plus features for input, output, and character handling, and design those features in a manner appropriate for the domain. which in our case was the programming of engineering applications. Next, define a library of subroutines to carry out the features missing from the Dialect for System Programming. Name it the Library of Machine-Dependent Routines, LMDR. GENESYS needed just 11 such routines. Implement a version of the library for each targeted computer using the computer's dialect of Fortran. A typical implementation of the 11 routines was just 220 lines of code in total. And then write the system using only the dialect of system programming, making calls on the library of machine-dependent routines. And finally, in the same manner, write a compiler for GENTRAN that translates GENTRAN into the dialect for system programming and includes calls on the library of machine-dependent routines. Then, an application written in GENTRAN can be compiled into Fortran and thence into machine code and linked to the computer's version of the library. Job done. Well, not quite. The recipe worked well for all machines except the ICL 1900 computer. While we were starting to work on GENESYS, Barry was completing work on a contract we had from Freeman Fox and Partners and the Ministry of Transport. The MOT's approach to developing software for more than one computer was to get it working on one and then adapt it as necessary for others. One product sponsored by the MOT was the British Integrated Programme System for Highway Design, a name universally shortened to BIPS. We had been contracted to get it to work on the IBM 360 and the ICL 1900. Barry succeeded on the IBM 360, albeit only by dint of preparing 285 job control cards, a story that made its way onto the pages of Computer Weekly. But the problem Barry hit with the ICL 1900 Fortran compiler was more serious. Here is a letter I was sad to have had to send to ICL, observing that we had wasted 7 weeks of effort trying to discover why things were not working on 1900 computers. Barry discovered that there was an unpublished limit of around 200 subprograms in any one Fortran program. And what is worse, the possibility of such a limit had been denied in spite of documentary evidence. And this made us very nervous that there may be other unpublished limits that could hit us further down the road. The problems were eventually put right, and GENESYS was made to work on the 1900 series, but not until much later than had been planned. With portability under control, all that remained was the minor matter of implementing the system. The syntax of each area of data was formally defined in the GENESYS reference manual, but we never compiled an overall syntax of the complete system. I thought it about time that we did, so for this talk I used the definitions in the reference manual to define the overall grammar. And it turned out to take almost 20 pages, have 176 productions and more than 200 keywords. For comparison, the grammar of the original version of Java had 117 productions and 50 keywords. We decided to parse all areas of data, including GENTRAN code, using a single lexical analyzer and a single syntax analyzer. We employed table-driven logic using a technique known as Floyd's productions. The parser converted data, whether code or lines of table, into a uniform internal structure, what we would nowadays call an abstract syntax tree. And each area had interpretive logic to walk its own region of the tree and take appropriate actions such as generating rows of a table, obeying a command, or omitting Fortran. We knew that this approach would not produce the fastest execution times, but it was an example of the policy we had identified on day one: make it work and speed it up later. I'm sure you're all familiar with the 3 rules of optimization. We were keen on instrumentation. Here is a typical final page of output from a GENESYS run. We were honest about the time taken by garbage collection, something some more modern systems could do well to replicate. Computer costs were mounting at SIA, and we decided to replace the portability layer written in Fortran with an equivalent version written in assembler. This would not only save money, but would be a useful dry run for a process that we imagined would take place for every computer that GENESYS was widely used on. Only one member of the team left during production of GENESYS, and that was Eileen Aldcroft. This was a serious loss. Eileen was our second employee at Engineering Computations. Eileen had recently got married, and she and her new husband had decided to both join the Technical Centre at SHAPE in The Hague. As Eileen's immediate boss, this meant that I was visited by an unnamed gentleman from an unspecified branch of the security services. There were questions such as, how does Eileen act at parties when she's had a drink or two? Now, we were a bunch of 20-somethings in the West End of London in the swinging 60s. How on earth was I supposed to answer a question like that without prejudicing Eileen's prospects of getting the job? I cannot remember how I answered, but it seems that nothing said was too damaging. As the only subcontract we let while developing GENESYS, we asked Eileen to write a CDC assembler version of the 220 lines of Fortran forming the library of machine-dependent routines. Eileen hired time on a CDC computer at a bureau in the town of Rijswijk. By using the computer in the early hours of the morning, she was able to keep development costs down and get several runs each night. And here is a page of the assembler that Eileen delivered. The CDC 6000 range had a 60-bit word and instructions that were 15, 13, 30 or 60 bits long. The left-hand column here shows how short instructions were packed several integers into one word. Each 15-bit sequence is displayed as 5 octal digits. All of Eileen's assembler code was meticulously commented like this, and it all worked perfectly. It also came with a set of notes that documented the code and included flowcharts for the trickier items. Now, it turned out that Eileen had decided to rope her new husband into helping with the project. And when we inspect the cover of the notes, we see the name of the gentleman that Eileen had decided to marry. It is none other than the CCS's very own Nigel Benet, the man who has built the arithmetic unit of the EDSAC replica. In the summer of 1971, the team at the GENESYS Centre were pleased to receive a version of the system for the RICL 1900 on the campus of Loughborough University. Their pleasure steadily turned to dismay as the size of their jobs increased. Here is a table showing that it could take 6 or 7 times as long to compile GENTRAN into Fortran as to compile the resulting Fortran into machine code. We had known that our strategy of making it work and optimizing later would not deliver a fast compiler, but we had been beguiled by the speed of the CDC computer into thinking that the speed would be sufficient. These figures from the 1900 told us that something needed to be done. Everybody agreed that the GENTRAN compiler needed to be revised in a substantial way. The question was how? You may recall that we'd converted GENTRAN into Fortran by using a generic table-driven parser to build an abstract syntax tree in memory, and then we walked the tree to generate the Fortran. Some in the team felt that improvements to this process could achieve a sufficiently useful improvement in speed. I felt that this would not be good enough. It seemed to me the problem was sufficiently serious that it could be fixed only by a complete rewrite of the GENTRAN compiler using a single pass with no data-driven logic and no interpretation. Furthermore, if this was to have any chance of being done quickly, it would have to be done by one person, and that person would have to be me. It was a shame to abandon the collegiate approach to design and implementation that had served us well. My decision was not universally popular. But here is a snippet from the rewritten GENTRAN compiler. There were plenty of words to describe its overall shape and structure, and then came flowcharts for every component, from which I wrote the Fortran code. The compiler was single pass, top-down, with precedence logic to compile expressions. And here is evidence of a bug not discovered until testing. I was relieved to see 50 years later that I'd done the right thing and corrected the flowchart also. The effect of the rewrite was a compiler that was an order of magnitude faster than our first version. Compiling a GENTRAN program was slower than compiling a Fortran program, but by an acceptable amount. As we reached the end of the project, we were all pretty weary, but there was still one job outstanding, the writing of the definitive reference manual. And as chief programmer, that was down to me, but I was exhausted. It was decided, and I do not remember who decided it, that I should go somewhere where I could not be contacted so that I could write the manual in solitude. It was also decided, I do not know how or by whom, that the somewhere would be Florence. And so it was that for a fortnight during May 1972, each day I would cross the Ponte Vecchio, head towards Fort Belvedere, and sit on these slopes in the Boboli Gardens at the back of the Pitti Palace and write. And I returned to London with a completed first draft of the 140-page reference manual. I rather regretted that Don probably wisely decided that the reference to our mythical Florentine office on the cover needed to be dropped. With GENESYS done, the team stayed together for a short while, but eventually most of the team left to form what became the successful independent software house, PSI. And Alan Register became its managing director, and Don and I continued alone as Alcott, Shearing and Partners. Our original quotation to build GENESYS was £100,000, but we overran the budget and billed a total of £130,000 over the 30 months it took 10 of us to finish the job. When the contract came to an end, the most senior civil servant responsible for the project took Don and me for lunch at the French restaurant L'Étoile in Charlotte Street, just north of Soho. It's still there. Note that he took us to lunch. In those days, there was no question of us taking him, even though we no longer had any financial or other links with the ministry. Towards the end of the meal, he said, "You know, you two have caused me the most immense trouble." We wondered what was coming next. He explained that when a project came to an end, details of its costs were circulated within the ministry, together with original estimates. "Since circulating the final figures," he continued, "my phone has not stopped ringing with other departmental heads wanting to know how I'd done it." It turned out that the ministry had never been involved in a software project that had had less than a 100% overrun. A mere 30% was unheard of. If only we'd been more savvy businessmen, we could have avoided all those sleepless nights and probably made rather more money. The final twist was that the total bill was only 6% more than our internal 1969 estimate had been, the estimate that we had fiddled downwards to meet the £100,000 figure we'd been advised to aim for. Meanwhile, the GENESYS Centre had started to advertise the system and its initial clutch of 5 subsystems. There was a licence fee of £100 a year to use GENESYS at a computer bureau. The Bureau added 10% to its charges and sent the surcharge to the GENESYS Centre. This was 5% if you wrote your own subsystems. To use GENESYS or its subsystems on an in-house computer invoked an annual licence fee for GENESYS and another for each subsystem. And the fee depended on the size of the organisation. And there was a half-price offer for anyone signing up during the first year of GENESYS Centre's operation. Universities paid a flat fee of £100 a year, and a computer bureau paid nothing for making GENESYS available as long as it added the surcharge and remitted it to the GENESYS Centre. The GENESYS Centre produced regular newsletters. It is a credit to the talented team that I was privileged to lead that this item appeared in a 1975 newsletter. The GENESYS system has never been down since its release. To achieve such reliability in software that worked across so many disparate computers and operating systems was a singular achievement. The GENESYS Centre had started on the campus of Loughborough University. In 1974, The NRDC formed GENESYS Limited as a wholly owned subsidiary with an initial capital of £50,000. The new company moved into offices in Loughborough and acquired the first Prime 300 computer in the country. They had to hire a crane to get it through the window of their fourth-floor offices. It was gratifying to learn that the portability kit we had originally designed for mainframe computers of the 1960s appeared to work equally well for porting the system onto mini-computers of the 1970s. GENESYS Limited had success both here and abroad. Here is a picture of an installation on a Prime computer in Riyadh in 1977. By 1982, organisations like GENESYS Limited were seen as quangos and hence undesirable. GENESYS Limited was sold to Quest in Dorset, and many of its staff moved from Loughborough to Ferndown. 3 months later, Quest went bust, and the receiver sold its assets to the Marconi division of GEC in 1983. Marconi had even less experience of, or interest in, engineering software of the GENESYS kind than Quest had had, and GENESYS gradually faded away. Here are some entirely personal thoughts about why GENESYS had a useful life of only about a dozen years. The Ministry of Transport had nothing to do with the design or subsequent development of GENESYS. Various local authorities got together and developed a program called MOS, which stood for Modelling of Surfaces and Strings, and it was widely considered to be technically more advanced than GENESYS Highways. MOT allowed their software, which included MOS, to be used without charge. A subsystem for finite element analysis was never written, even though at least one offer was made to produce one. Portability of Fortran gradually improved, mainly because computers with word lengths of 24, 36 and 60 bits left the scene. Many consulting engineers bought their own computers, usually primes, and with an in-house computer, portability became less important. Above all, in my view, GENESYS did not evolve. Except for minor tweaks, several plans for a GENESYS 3 never got off the ground. Languages need to keep moving, as we saw with the 11 dialects of Fortran. That's a new dialect every 6 or 7 years. 2 months ago, version 17 of Java was published. That's a new dialect every 18 months. I'd like to present a brief look at what has happened to engineering software since GENESYS. The emphasis is not now on just analysis and design, but rather on the maintenance of the assets constructed with the help of analysis and design programs. And to illustrate this change of emphasis, first consider what it was like to use the Highways subsystem of GENESYS. Here is a ready reference for the subsystem, written by Don in the style that he would later make his own in a succession of handwritten books. First, the engineer defines levels of a rectangular region of the terrain to be traversed on a motorway. A block command incorporates the levels into the terrain model. Next, the engineer defines the geological model, including interfaces between topsoil, chalk, clay, and rock. Then comes the alignment of the proposed road. This defines the spine of the road in three-dimensional space. Different regions of the spine can be defined in different ways. And then cross-sections are defined along the road like ribs hanging from the spine. As more complicated aspects of the model are added, the grammar of the commands becomes more elaborate too, allowing not just alternative paths but repetition. The grammar of a GENESYS command was a directed graph of clauses in which each clause started with a unique keyword and there were no ambiguities in choice of path. A GENESYS command had a type 3 Chomsky grammar. Finally, the engineer could use a print command to choose outputs. The results were line printer listings with endless columns of numerical values. In contrast to the way highway designers used computers in the 1970s, I'd like to tell the story of a system called HAPMS, introduced in the year 2000 by the Highways Agency, an organisation that became Highways England and is now National Highways. HAPMS is short for the Highways Agency Pavement Management System. Our pavement is a construction for bearing traffic that uses bituminous materials with aggregates, concrete or both. It is not just a sidewalk. Vehicles like this travel the country's trunk roads continually. They're equipped with lasers and other gizmos that measure and record conditions such as ruts and cracks, skidding resistance and stiffness. And the data are fed into HAPMS. An associated system called SWEEP extracts data from HAPMS and analyses alternative maintenance schemes. As a consultant to the Highways Agency, Barry designed HAPMS and was responsible for the design and implementation of SWEEP. And Barry wants me to stress how much he relied on the skills of his excellent teammates. In 2007, Barry asked me to join his team, and thus arose the delightful situation of Barry working for me in 1970 and me working for Barry 37 years later. He asked me to work on the efficient handling of huge volumes of data and the efficient generation of complex graphical reports. Outputs from computers today are nothing like the endless columns of numbers produced by a GENESYS subsystem. Here is output from SWEEP, showing a so-called strip diagram in which a portion of curved road is mapped onto a straight line. The bottom two strips show measurements of rutting and cracking for two of the lanes. Towards the top of the page is a rather strange graphic. It is the strip of an ordnance survey map containing the motorway, distorted to match the straight line. This was an experiment, and I was surprised by how readable and useful the distorted map turned out to be. More examples come from a SWEEP report that presents maintenance plans and costs. This report was 83 pages long. The cover page shows the extent of the proposed scheme, this time without distortion. And then a strip diagram shows the geometry of the region to be maintained. The SWEEP computational model is a formidable beast that explores alternative patterns of maintenance stretching 50 or more years into the future. Produced in 2007, this diagram shows planned maintenance and costs from 2008 until 2067 for one pattern considered in the report. It's heartening to discover that some corners of government have a rather longer perspective than just the next electoral cycle. Then followed many pages with isometric diagrams showing the type of treatment needed along each stretch of each lane. We achieved the objective of the project, which was to reduce the time to produce such a report from minutes to a couple of seconds, and to enhance the level of detail in the graphs and diagrams. To do that, I had to abandon the convenience of library software for generating PDF and instead write bytes, including the compressed form of each picture, in a single one-pass stream to the PDF output. Fortunately, PDF has a structure designed for one-pass generation. The index of a PDF file is at its end and not its beginning. HAPMS and SWEEP software operate on Windows servers with typically 30 online users. 14 years ago, there were 17 such servers, of which 12 were dedicated to SWEEP analysis and reporting. My reporting software was developed in C#, and the rest of the SWEEP software was written in VBA. The HAPMS and SWEEP software are still in use today, some 14 years after Barry and his colleagues designed it and I wrote the SWEEP reporter. How strange that the last software I wrote as part of my professional career has had the longest useful life of any that I've written, including GENESYS. However, the end is nigh. Some of the hardware on which HAPMS runs has become obsolete, as have some of the software tools used to build it. Highways England have let a contract to produce a replacement for HAPMS, but still using the underlying concept of the existing system. Now, I'd like to conclude with a very short codicil to the first GENESYS talk last November. You may recall that when we started to use the interactive system provided by Time Shearing Limited in Great Portland Street, the Telcomp interpreter was too slow to allow us to use Gaussian reduction to solve equations. Instead, we had to pre-evaluate the matrix arithmetic using only scalar variables and avoid using subscripted variables. Now, there's another way to say that. What I could have said was that we were pretending to use a computer that did not have an index register. And that was precisely what Charles Babbage had been doing 130 years earlier when writing programs of his not yet built analytical engine. An engine with many features of a modern computer, but without an index register. This sketch is in the National Portrait Gallery. And here is program L26, written at the beginning of August 1837. It is one of 26 programs now online in the wonderful Babbage archive at the Science Museum. 11 of the 26 were for linear algebra, mostly for solving simultaneous equations. Without an index register, solutions can be expressed in modern matrix notation in terms of the determinants of submatrices. And before getting stuck into simultaneous equations, Babbage wrote this program to flex his programming muscles by evaluating an isolated algebraic expression. An expression he chose was this one. Now, why did he choose this particular shape of expression over the myriad other simple shapes he could have chosen? I suspect that he knew where he was going in his choice, as the expression is close to being a determinant, the shape of expression he knew he would be needing as he progressed to solving complete equations. I find it intriguing that we were unknowingly echoing patterns of thought that Babbage had had 184 years ago, and that we have only learnt that it was an echo this year. And now it is time to thank friends who helped with this talk. The first thanks are to Richard Abel of the Transport Research Laboratory for help with the history and future of HAPMS. Next thanks are to Chris West, who worked at the GENESYS Centre for much of its existence. Chris provided invaluable insights into its history. And I'm happy once again to acknowledge the help of those members of the GENESYS team that I'm still in touch with. Alan, Eileen and Nigel, Barry, Dick and Graham. I'm sorry that I couldn't include more of your reminiscences. As you all knew very well when you retold them, most were entirely unsuitable for an audience like this. But thank you anyway. Finally, a special thank you to Betty, editor of both talks, and still my inspiration and support, 56 years after we first met in 21 Portland Place, where the GENESYS story began. Thank you for listening, and now back to the CCS recording studio in London.
Thank you very much indeed, Brian. We'll clap, but you'll probably have to imagine the sound it's all going to make. Hand over to Darwin to manage the questions from the real and virtual floors.
Can I take that microphone? This one is. Thank you, Rachel. I don't currently have any questions in the chat. If anybody does want to ask a question, if they'd like to unmute themselves and ask it, you're more than welcome.
So they met in 1960, 56, 65.
Is that a question? Somebody have a question there?
While people are thinking of possible questions to ask, one thing I'd like to add is that the only source of information I found about GENESYS are my own personal archives. You heard the story of the GENESYS Centre. It's just possible that something is in the GEC archives, if they've got an archive library, but there's nothing at all, as far as I can tell, on the web or anything like that. If anybody does have any other records, it would be interesting to have. Also, we've got about 10 feet of documentation here, and they're looking for a home. We've recently downsized, and the pressure is on to recover the space. So if anybody has any suggestions as to where these archives would usefully be placed for future researchers, I'd be interested to know.
I'll give it another few seconds if anyone does have any questions, but otherwise I will hand back over to Rachel.
Civil engineer. Yes, it's forcing to.
Okay, I will hand back to Rachel.
Thanks, Darwin. No further comments as well as questions? No? Well, Brian, thank you very much indeed for such an interesting and coherent presentation as the part 2, which we were all waiting for and were so pleased to have listened to, and your wonderful slides, which were so interesting to share with us. So thank you very much indeed. So can we all give Brian a round of applause again, please? So thank you very much indeed. Thank you all for attending today. And our next meeting, I'd like to tell you about 2 meetings. The next one is going to be on Thursday, the 16th of December, and will be a film show. And we won't be able to post a video of it afterwards. So this will be your unique opportunity to watch. And the second talk I want to tell you about is on the 6th of January, when we've been invited to listen to the great Vince Cerf, who is the originator of TCP. And it's the Archives of IT that he's speaking for, but the details of how you can join in that are at our website. So that will be a wonderful presentation to participate in. So I look forward to seeing you all at the film show and to listen to Vince Cerf. Thank you very much for attending.
Thank you.